Hello everyone. Today we are going to move on and talk about algorithms. Well, and I talked about this before, and the reason that we are learning algorithms in the data science curricula is in the second semester. You are going to see a lot of machine learning models, and when we are seeing the machine learning models, and we always have one discussion, that is the time complexity or how fast this machine learning model is. And I can give you an example. Say, well, when we learn the k-means, and we know k-means is a linear time clustering algorithm. And later, after a few lectures, and we are going to learn another clustering algorithm called dbScan. And I will tell you the dbScan is a O(n) cube algorithm. Okay, well, and say if you have a hypothetical scenario and you have 1 million xy coordinates, and then how do you want to cluster them? 1 million samples, just xy coordinates. And then if you say I want to try k-means, and then I will say, okay, that makes sense, go ahead and try that. And if you say I want to use dbScan, oh boy, you are crazy. I'm not saying the dbScan cannot be done, but you should know dbScan is really slow on the big data sets compare with k-means. And then how do we define what is fast and what is slow? And the knowledge you got to have is the algorithm. Okay, and well, remember the question we want to ask, the question we are going to ask and we are going to see again and again is for example, say if you run a small data set, and then well, it can finish in the time t. Okay, so t is a time that you can finish a sample data set. And now if you have 100 times of the data, and then how much more time are you putting to the running time so that you can get it finished? And if you say, okay, if we have 1000 times of the data, and then it is 1000 times of the original time t, I can finish this algorithm. That's not always correct. You are assuming that is a linear time algorithm to do that. Okay, and just now I say, well, I talk about the k-means, and yes, k-means is a linear time algorithm. This means, well, if you have 1000 times of the data, and indeed you just need to put 1000 times of the original time to run the big data set. But in a lot of the other machine learning models, that's not the case. Okay, so well, another reason I want to talk about this is when you are going for an interview, and then they may ask you some questions related to the algorithms, and they ain't gonna ask some really hard questions and ask you to design a really complicated algorithm if you're interviewing for a data science position. And however, they will challenge you just to make sure that you have the idea or you have the knowledge of the algorithm, or especially the time complexity of the algorithms, and you should have that. And well, in this curricula, well, we are going to spend the time. We will spend some time to talk about some algorithms and some evaluating some algorithms in our class. And if the interviewer challenge you some really hard algorithm question in the interview in the future, no matter if it's for the internship or for a full-time job, and well, shoot me email and talk to me about these kind of questions. And usually I don't see a lot of people saying they are interviewed, and and that company ask them to design algorithms in the interview for a data science job. It's not quite common, but they may ask you, why do you use this algorithm? And if you use another algorithm, is that going to be faster or slower? And you should have the idea about this. Okay, and for the algorithm, the biggest thing is called the big O notation. So for the big O notation, this is a standard language for us to describe how long an algorithm is going to run well, given a size of the input. Okay, and then it gives us the important information on how the runtime is going to grow when we have larger and larger input. So of course, the running time usually is related to the input. When you have a larger input, and then the running time will be bigger. And well, if it is a ON algorithm, and the ON means that is the linear to the size of the input, or it is it is on the square of the size of the input, and then that is the ON square algorithm. That means if you double the size of the input, and then you have to put 2 square time of the running time, so that is 4 times of the original running time. Well, and another thing we want to understand is we are not quite interested in the smaller size of the input. And what is small, what is big, it really depends on how fast your machine is. But usually when we are talking about the time complexity of the algorithms, and we are not interested in a machine learning model with 100 samples or 1000 samples. We are talking about probably tens of thousands or millions of the data. Okay, and also we want to talk about the worst case behavior. And usually for some of the algorithms, they have the best case scenario, average case scenario, and the worst case scenario. And we are considering most of the cases the worst case scenario. Okay, so that is the introduction of the big O, and probably you are still confused what is the big O. Hold tight, and I'm going to explain a little more after we get the Tn. Okay, so what is Tn? So when we are trying to find the running time of an algorithm, and by the way, an algorithm doesn't have to be something super complicated, and a piece of the code as small as this, well, this can be called an algorithm. Okay, and then when we have this kind of algorithm, how do we measure the running time? And of course, if you have a stopwatch, and you can just say, okay, hit the run, and then and then when it's finished, and again, right? And then you have the running time. But in the computer science world, we don't do this way, and we do another way. That is, we count the number of the primitive steps. Okay, so let me use this one as an example. So, we have a list, and then, and after that, we define the sum, and for each value in the list, and then we add that number to the sum, and then eventually we want to get the sum divided by the length. So what are we doing? We are getting the average of all the members in the list, right? And then let me ask another question. How many primitive steps are we doing? Okay, this might be a little bit harder. Say, this one, for the definition, we count that as one primitive step. Okay, and then for this one, we define a sum, so that is another primitive step, so no problem. And how about this one? Well, for I in nums, even though this is just one line of code, and we should know that is an iteration, and this is going to run for how many times? It depends on how many values we have, right? So let's say we have n values in the nums, and then this line is going to run for a total of n times, and each time we are going to pick one value. So each time we run it once, we pick one value, but remember, we are going to do a total of n iterations. Each time we run this line of code, and then we grab one value from the list. And the next line, again, it's going to run for n times. So 1 multiplied by n again. So each time, we are going to add this value to the sum, and then we assign that to the sum. Okay, so eventually we have this line. And then that is 1 again. Okay, so adding together all the number of the primitive steps I have already put down here, and then eventually we have this. So that is, for this Tn, that is given the input size to be n, how many primitive steps is required for us to finish this algorithm? And ta-da, we have the answer. And that answer, Tn, is a polynomial of n, right? So 2n plus 3. Okay, so let's do another one. Okay, well, this time we still have the nums, and then we are going to have the sum of the product. So we are exhaustively try to grab two values with putting back. So we have a bag of the values here, right? And then we are grabbing two values with putting back. This means we can grab the 2.9 and the 2.9 again. So I can grab two values, and then I want to get the product. And after getting the product, I want to add that to the sum of the product. So how many primitive steps are there? And okay, if we want to count again, this one is 1, and this is another one, because those are two definitions and we count them as two different primitive steps. And the tricky part started here because now we have a nested iteration, right? So say we have this one will run for n runs for next two lines. So each round we are going to say this one will run for n rounds, and this one will run for n rounds, n rounds and n rounds. So well, those two lines will run for two n rounds given each of the n value. Okay, so this one runs for n rounds, so this one should be a multiply by n. This one should be multiplied by n because that is the n rounds for this iteration. However, since this is the inner iteration, put into an outer iteration, so this will be counted as the n square rounds and n square rounds. And eventually we are going to have this one as a 1. So 1 plus 1 plus n square plus n square plus 1. So we got 2n squared plus n plus a 3. And that is the Tn. That is how many primitive steps we are required to finish this algorithm. Okay, so for this one, for both Tn, they are the polynomials of the n, and we have the 2n, we have the 2n squared. So if you just visually check those two polynomials, and remember, when we are talking about the growth, that Tn, the difference on the Tn will result in the difference of the running time growth when the input n is growing. Okay, so just now we talk about the Tn, and for the Tn, well, the concept is very simple. We are counting how many primitive steps are required for us to finish a algorithm, and that is the Tn. And the next lecture, we are going to talk about how we can move on from the Tn to the big O. And we are going to later in this course, and then in the next course, DSC 522, we are going to most of the time we are using the big O to measure the running time or the time complexity of algorithms. So I will see you in the next video.